Hello everyone, this is Priyanka Sutar, Assistant Professor of Gellert Institute of Pharmacy, and today I am going to discuss reactions of pyrrole and indole. Okay, before starting to learn with the reaction, let's have a look at the structure of the pyrrole. Pyrrole is a five-membered aromatic ring which contains one heteroatom, and that heteroatom is nitrogen. So here it is the structure of a pyrrole, which is a five-membered aromatic ring, which is aromatic ring. Now this is the aromatic ring, and nitrogen also has a lone pair which is a part of the aromatic structure, and it contains one heteroatom. Just remember the numbering starts from the heteroatom. Now you will see various reactions like electrophilic substitution and reduction reactions of pyrrole. So before we learn the reaction, let's have a look at the rule of the electrophilic substitution. If you see electrophilic substitution, the pyrrole undergoes electrophilic substitution preferentially at second carbon. Now this depends on charge distribution, that is a negative charge distributed over the structure of the pyrrole. It is mostly at a second, third position mostly. So there are two chances that it will be substituted at second or third position, but the substitution which is there, it occurs preferentially at carbon number 2, because if you see 2 substituted pyrrole and 3 substituted pyrrole, 2 substituted pyrrole is thermodynamically stable. That's why it is preferred, and it can be rationalized by seeing the transition state, stability of the transition state. Two substituted products are having higher stability of the transition states of the product, hence that is a preferred. So you remember just one thing, electrophilic substitution in the pyrrole will occur at second position. You will see that there are some exception. This is a basic rule that electrophilic substitution of the pyrrole will occur at carbon number 2, but you will have to learn the you will have to remember the exception. There are few exceptions we will discuss. So starting with the first reaction, that is chlorination. We will see halogenation, nitration, sulphonation, and we'll start with the chlorination. Chlorination with the thionyl chloride. Now here reagent is important. Okay, depending upon the reagent, product is there. Okay, so as the reagent changes, the product will also change. If 1 mole of pyrrole react with 1 mole of thionyl chloride, it will form a 2-chloropyrrole, and the same pyrrole reacted with the 4 molecules of thionyl chloride, then it will form a 2, 3, 4, 5 tetrachloropyrrole. Means all carbons will be substituted, all carbons will be substituted with the chloride. Means halogenation takes place at 4 carbons. Now bromination, again here there are two conditions. Bromine in carbon tetrachloride, it will give 3 bromopyrrole. Now you have learned that electrophilic substitution occurs at second position. Here also electrophilic substitution will occur at second position, but this 2 bromopyrrole which is there, it is not stable, so the structure itself gets rearranged and it forms a 3 bromopyrrole, which is much more stable product. Now moving on to second reaction condition, that is a bromine in acetic acid, acidic condition. Bromine in acidic condition, it forms a 2, 3, 4, 5 tetrabromopyrrole. Now you see the difference. Chlorination, subtle change in the change in the reaction condition changes the product. Next is the iodination. Iodine plus potassium iodide will give you again 2, 3, 4, 5 tetraiodopyrrole. Next is a nitration reaction. Now here there is a exception again, because pyroles which are there, they are sensitive to acids, and that's why they cannot be nitrated with the strongly acidic condition. So here nitric acid in acetic anhydride is used as a nitrating agent at low temperature, so it will give you 2-nitropyrrole. So instead of acidic condition, it will use acetic anhydride. Then sulphonation will take place in presence of reagent pyridine sulfonic acid at 100 degrees Celsius. It will give you pyrrole 2 sulfonic acid. So here you can see that electrophilic substitution will occur. Electrophilic substitution will occur at second position, that is the preferential position for the electrophilic substitution is carbon 2, but there are some exception, like depending upon the reagent it forms a different product. Okay, so but mainly the substitution will occur at second position. Now moving on to the second structure, that is a benzo fused heterocycle. It is a 5-membered aromatic heterocycle which contains one heteroatom, that is a pyrrole, which is fused with benzene. Okay, so benzene plus pyrrole. So pyrrole is fused with its B phase. B phase of pyrrole is fused with the benzene, gives a structure called as a indole. Now we have just seen the electrophilic substitution in the pyrrole, and now we will see how the fusion of benzene affects the reaction. Okay, so we are going to learn reactions of indole. Electrophilic substitution, because of fusion of the benzene ring, there is a little bit change in the reactivity of pyrrole. Because of the fusion of the benzene ring with the beta phase, there is a deactivation of second position for the electrophilic substitution. So what happens, there is a change in the distribution of the negative charge, right? So that negative charge, that means the electron density is shifted to more towards the third position. That's why here indoles will be electrophilically substitution, sorry, electrophilic substitution of indole will occur at position 3 instead of position 2. Third position there will be electrophilic substitution. So starting with the halogenation of indole. First is iodination. Iodination, here you see reaction condition, either iodine in CHCl3 chloroform or iodine in DMF at low temperature. Now what is the rule? It will be substituted at third position. So you see the product which will be formed, it will be 3-iodo-indole. So the electrophilic substitution or halogenation is at third position, 1, 2, 3. So iodine will be attached to the third position. Now chlorination, here again reagent used for the chlorination is thionyl chloride, and again because the electrophilic substitution will be substitution of indole, you will see it will be substituted at third position, so product will be 3-chloroindole. And we have seen previously in excess of thionyl chloride it will give different product, right? Now here two positions of the pyrrole are fused with the benzene, so only second and third carbon of the pyrrole ring will be substituted, electrophilically substituted, that is it forms a 2,3-dichloroindole. Bromination will take place at third position, giving you 3-bromoindole. Bromination in ether will give different product. Now here it is a exception. Okay, mostly electrophilic substitution of indole will occur at third position, but if third position is occupied as in this particularly in this structure, third position is already occupied by a substituent, that is a methyl group. So now here electrophilic substitution will occur at second position. This is general rule for all electrophilic substitution. Preferential position for electrophilic substitution is third position, but if third position is occupied, then there will be electrophilic substitution will be at a second position. So you will see 2 bromo 3 methyl indole. It will form a structure 2 bromo 3 methyl indole, and again the solvent is also changed because of there is a substitution. Much different conditions are required. Now here it is a different reaction, that is Willsmere-Haag formylation. Formylation will again take place at third position, forming a indole 3 carbaldehyde. Then nitration, as we have seen previously, that pyrrole ring which is there, it is sensitive to acid attack, right? It is sensitive to acid. That's why we cannot use strong acid for the nitration. So we are using here different nitrating agent, that is a benzoyl nitrate in acetonitrile, and it will give again the same compound, that is 3 nitro indole. Sulphonation, it will give indole 3 sulphonic acid. Mannich reaction in presence of indole in presence of formaldehyde and dimethylamine and acetic acid, it gives it is a aminomethylation. Then reduction reaction. Now reduction, if you see the indole ring, if reduction reaction is there, the double bond will be reduced to a single bond, giving rise to 2,3-dihydro indole. It is not 2,3-dihydro, it is 1H 2,3-dihydro indole. Then another reducing agent used, that again it will give the same product 2,3-dihydro indole. It is not 2,3, it is just 1H 2,3-dihydro indole. So if you see electrophilic substitution in the indole take place at third position, okay, and what you say, in case of pyrrole, electrophilic substitution will take place at a second position. But there are some exceptions, like change in the reagent, it will change the product. You can see over here. Here is a change in the reagent changes the product. So you remember the basic rule. You have to remember the basic rule. That is. So you remember the basic rule that pyrrole will be electrophilic substitution in the pyrrole is at second position, and electrophilic substitution in the indole is at third position. But there are some exceptions. Okay, so you remember the basic rule and you remember the exceptions. So it is easier for you to remember. Now I would like to say thank you for listening to this class, and I also suggest to practice this structure. You can take screenshot of particular this, and once getting a screenshot, you can also write it down so that you remember. Now one thing is there, that if you use your logic, you don't have to practice. If you know the rules and exception, then you don't have to practice. You need to just remember the basic structure. Then you remember the rule that indole is electrophilically substituted at a third position, and you also need to remember the reaction condition. That's it. So thank you for the listening the class. All the best. Bye.